Well, let's get started. The presentation this morning will be given by Dr. Dan Gillins, a geodesist for NGS. He's a licensed land surveyor in Oregon and in Utah. He is currently the project manager for developing guidelines for conducting height modernization surveys with GNSS, as well as developing software for processing and adjusting differential leveling data. Prior to working for NGS, he was a professor for civil engineering at Oregon State University, as a land surveyor for 10 years for the Bureau of Land Management and U.S. Forest Service. Dan Gillins serves as Vice Chair of the Survey Division within the American Society of Civil Engineering and as the Director of the American Society of Geodetic Surveying.
I'd like to just start by saying good morning, and I'd like to thank ODOT and the Geometronics and I guess more specifically Chris and Randy for helping to set this up today and for the opportunity to give this presentation. I'm pretty excited to give it. It's actually the first time that I've presented this material, so I hope it goes well, and I apologize in advance if it's choppy in certain places. I just wanted to start by saying, if you have any questions, please feel free to ask. I'd very much like to answer those at the end of the presentation. Next slide. Okay, I realize today's presentation is on RTNs, but I wanted to start by just giving a little bit of background on leveling, and you may wonder why are we starting there, but hopefully it'll make sense as I go. For many, many decades, NGS has primarily relied on differential leveling for establishing high accuracy vertical control. And that's because leveling, especially over short distances, within like say a few kilometers, is extremely accurate. You can even get down to sub-millimeter accuracy in measuring height differences. The problem is it's a tedious process, and as a result, because it's so tedious, it's prone to user errors. Another challenge is you must begin by leveling from a mark with a known height because you're only measuring height differences. So for, let's say, next slide. So for quite some time, NGS, and continues to do so today, provides known heights to surveyors. So heights on these things, passive marks or benchmarks. So if you wanted a height reference to our National Spatial Reference System, you need to go out and find these marks on the ground and tie your survey to them. The way that we derived the heights on these benchmarks was back in the late 80s and early 90s. We combined over 700,000 kilometers of leveling that had been done primarily since the 1920s. From the 1920s to the 1980s, and we combined all of these leveling lines across our nation into that were between over 500,000 monumented benchmarks. Combined it all into a single network, and then we held the mean water elevation of a tide station in Canada, set its elevation equal to 0, and then we did a massive minimally constrained least squares adjustment. And the resulting heights on these benchmarks were what we use today, and actually realize what we call the North American Vertical Datum of 1988. So if you wanted to tie into NAVD 88, this is the physical manifestation of it on the ground. You go and find these marks and tie your survey to it. Okay, so next slide. As this slide, oh, okay, it came up quickly, great. I mean, this is actually a map of all of the differential leveling that is currently in our database. The overwhelming majority of it was there prior to the realization of NAVD88. And you can see first order leveling is in red and second order leveling is in blue. If you look at the map, say in Oregon, there's not quite as much leveling done there as some of the other states that have been more active in doing second order leveling, processing that leveling, and then submitting it to NGS for adjustment and inclusion in the network. We still have states that are doing that today. Probably the most active state right now is Minnesota. Next slide. There's some challenges with this system that we realize, we've come to learn, and they remain today. First off, it seems, it's amazing to me, I mean, how many surveys I've been on where the benchmarks they never seem to be where you want them to be. They're not in a convenient location. They're not near your project area. If you want to tie your survey to them, often you have to travel great distances to tie into them. Another challenge is because they're spaced out and quite distant from one another, you generally have to assume the benchmarks have not moved. One way to account for that is maybe to level or measure into several benchmarks and see how well these few fit together, and if they all fit together fairly well, then you assume that they're stable. But we know the benchmarks have moved. Everything is moving. The heights that we derived on these benchmarks were done in the early 90s. It's been over 25 years since NAVD88 was realized, and the Earth's crust is just not fixed in place. So everything is moving a little bit. Another challenge is the benchmarks are often destroyed and rarely replaced. There's definitely a sparse number of them outside of the continental U.S. And then the heights for the benchmarks were derived from a single point, which allowed error to build up across the country, and actually Oregon and Washington actually have the largest amount of error in our leveling network. Next slide. So our goal at the National Geodetic Survey is that in 2022, which is 5 years from now, we will replace NAVD88. We will move away completely from this current reference and this current datum. And the big change, and this is a pretty huge change around here for us, is that our vertical datum will no longer be realized by leveling between passive marks. Instead, the idea is that if you want to do a survey and tie it to the National Spatial Reference System, you will use, the primary axis will be using GPS or GNSS. And then from your GNSS observations, you correct it by using what we're working on right now is this very high accuracy gravimetric geoid model, which is going to be named Geoid 2022. So if you want to, I've got a nice little illustration on the next slide. Maybe it can help with showing this. So say you're working someplace and you want to derive a height, and in this case, I guess more specifically, an orthometric height on some station in the past, and you wanted to tie that to the National Spatial Reference System. So in the past, what we would tell you is, okay, now what you need to do is go and level to nearby benchmarks, tie into those, and do an adjustment, and that will give you the highest accuracy possible for an orthometric height at that station. In the future, what we will be telling people is instead, they'll set up a GNSS receiver on that mark, next, and then take a GNSS observation or conduct a session, next, and what that will return is a ellipsoid height, so some normal to the reference ellipsoid, so you can get an ellipsoid height directly from your GNSS observation. And then at the latitude and longitude of that station, you can look up a geoid height from a geoid model. So you click next 2 more times. Okay. So in this diagram here, I'm showing the geoid beneath the ellipsoid, which is the case in Oregon. And so in this case, n is a negative number. So you could look up what that separation or the geoid height is from Geoid 2022, And then you just simply take and combine those two values, and that will give you your orthometric height in purple. So if you click next, you have your simple HHN equation, h equals h minus n, and next one more time. More specifically, the way you will get an orthometric height in the new geopotential datum of 2022 is you'll take your ellipsoid height, which will be in this other datum, the horizontal portion of our datum. That's going to be its official name, NatRef 2022, and then you'll difference it with the geoid height from the geoid 2022 model. So we're going to assume, for the purpose of this presentation, that the geoid modeling is done perfectly. And NGS is building a geoid model, and we're not going to worry about it. We're just going to use it. So the focus today will be instead on how do we derive high accuracy ellipsoid heights, or little h, or the green value, so that we can then combine it with the geoid height and then get an orthometric height. That's what we're driving at. So how do we get an ellipsoid height as accurately and as efficiently as possible with GNSS? As a surveyor, how should we be doing that? Okay, next slide. Okay, so there's a lot of advantages of going to this new system. I mean, first off, it's easily accessible simply by making a GNSS observation. So you can establish vertical control in any convenient location. No longer do you need to find an existing benchmark. Once you've established that control, then you can then level from it, or set up a total station or an RTK-based station on it, and then go about your work in your project area. It's also possible you could derive an orthometric height on marks at the time of your survey, which will be a big change because you can take the ellipsoid height measurements at the time. Of course, those are at the time of your survey, at the time of your GNSS observation. And then we have a geoid model that will be time dependent, and so you can actually derive orthometric heights at any mark at any time, or at the time of your survey, I should say, which would enable you to actually monitor orthometric heights at marks. Okay, next slide. So there's been a lot of chatter, and hopefully by now you've heard that National Geodetic Survey is planning to replace NAVD88 and actually also NAD83 with new datums. Hopefully those presentations are happening in your state. I'm quite confident they are. And there's a lot of talk about it, and I like to, if I could, I'd like to try to boil it down into a single slide, and that's what I'm trying to show here. And the National Spatial Reference System, really, as a surveyor, to me it has two components that we should care about. Okay? And the first component is the horizontal component, which is maybe a little bit unfortunate because it's actually more than just horizontal. It's latitude, longitude, and also ellipsoid height. And the way we will be defining that reference system in the future will be, it's just the cores. So if you tie your survey to the cores, your latitudes, longitudes, and ellipsoid heights will be within the National Spatial Reference System. And then the other component is the vertical, the orthometric heights that I just showed in that diagram. And those will just be simply obtained by taking your ellipsoid height from GNSS and then subtracting your geoid height from geoid 2022. So you could boil it all down into, as the cores will define your horizontal control, and geoid 2022 will define your vertical. And that is really what it is. Okay, next slide. Okay, within NGS, we've over the last few years, we've worked on developing software to help you with managing your survey data and derive high accuracy ellipsoid heights. And this is called Opus Projects. I know you had Mark Armstrong, before he retired, gave a number of trainings on this program to surveyors in Oregon. And hopefully this program is something that you are starting to integrate into your workflow. If you want to tie in to the NSRS, this is our kind of our premier software program, the best version of Opus. And it's free, it's web-based. Currently it's designed for processing static GPS observations. That's going to evolve, and I'll talk about that a little bit at the end. It's meant for managing a survey of multiple control stations, and it's meant to help you tie your survey to the cores. So you can pick which cores you want to use, you can process the lines, establish your control. Geoid models are all included within it. And right now we are working on developing a path so that you can, once you've done your processing and adjustments in Opus projects, you can submit it to NGS, and it will be loaded into our database and published in the integrated database. That development is actually almost finished. We're expecting it to go to beta within a month or so, so we're very close to done with that. Next slide. Okay, click me one more time. All right, so the problem at hand and what the purpose of my presentation today is that although Opus Projects is a great tool, right now it really requires lengthy static sessions. The minimum session duration for Opus Projects is 2 hours. You have to do at least a 2-hour session on a mark just to get the data loaded in Opus Projects. But really what I've found from my own testing is if you care about ellipsoid heights, if you're trying to get high accuracy ellipsoid heights, you really should be observing marks for a minimum of 4 hours, 4 to 5 hours. Horizontally at 2 hours it's fine, but vertically you can get a lot of noise in your solution. From additional testing, I've also found that you really need 15 hours if you want to drive the ellipsoid heights to an accuracy of less than 2 centimeters at 95% confidence. And so I'm going to point out 2 centimeters at 95% confidence because that's kind of the standard we use right now for a geodetic height modernization survey. So that's the goal. We want 2 centimeters at 95% confidence. Okay, next. But of course, that's a long amount of time to be observing marks. And if you have several control marks in your project, that may not be tenable, especially today when we're so accustomed to using RTK and RTNs. We can get quite accurate solutions in as little as 5 seconds. Maybe you do a 3-minute shot or an 8-minute shot, I don't know, but whatever it is, we can get centimeter level accuracies with RTNs. Another beauty is that you can check your solutions in real time. You can take repetitive shots on marks, inverse those in near real time, and see how well your work is going instead of having to wait to post-process. So it's clear that RTNs and RTK surveys might be sufficiently accurate for a number of geodetic applications. And so kind of the research question that we're trying to answer and what we're trying to study here is, what is the accuracy of RTK and RTNs, and how can we make use of it in geodetic surveys in conjunction with Opus? Okay, next. Okay, so RTK surveying has been around for a long time, and I probably don't need to spend a lot of time talking about this to this audience because I think most likely everyone on the call has executed an RTK survey. But the conventional mode is you set up a receiver over some known coordinates, and we call that your base station. Then you have another receiver, your rover, you're moving around throughout the day taking measurements. One key thing worth mentioning is you really should stay within 20 kilometers or about 12 miles of your base. As you get further and further away, some of the tropospheric areas don't cancel, and those areas can build up. There's a number of applications shown on the slide that it's used in. Okay, next. And then, of course, we could take it a step further now and say, okay, well, instead of setting up a temporary single base station, what if we build out a network of base stations that are permanently operating? And in Oregon, such a network is available, and of course ODOT manages it, and that's the Oregon Real-Time GNSS Network. As I've been studying RTNs, what I found is kind of the recommendation is that you keep your base stations in your real-time network within 70 kilometers of one another. That seems to be a pretty consistent message that you hear from vendors. And then based on that, you can infer that the baseline lengths could be as much as about 40 kilometers. You're never more than 40 kilometers from one of the base stations in the real-time network. The advantage of a real-time network is that the atmospheric errors can be interpolated between multiple base stations. So this little diagram at the bottom of the slide shows two scenarios. You have a single base RTK on the left, so that's just using a single base station. And I'm going to call that throughout this presentation, this survey method, SRTK, to stand for single base RTK. In that mode, you only have one data point for modeling atmospheric error. Whereas in network RTK, like shown on the right, this little diagram, you have a few base stations or more that you can interpolate the atmospheric error between, and therefore it helps model the actual error better. So network RTK, what I'll refer to as when you're using the full network corrections from the RTN, or NRTK, as opposed to single base RTK where you're only using a single base station. Okay, next slide. Here's just a quick background, and you know, I've since decided I probably should have added more information on this, but I have a feeling that maybe you'd rather not hear about all this anyway. There's really two ways to two very common ways for an RTN to provide network corrections. Okay, the one on the left is the VRS idea, virtual reference station. That's actually primarily used by Trimble networks. And in the VRS method, what you do is you can see the surveyor standing there holding the rover. When he turns on his receiver and connects to the RTN, it computes a point position somewhere nearby, usually within 5 meters of him. And then it takes that coordinate and it submits it to the central server. And then the central server does some interpolation of the nearby RTN base stations and assigns it to that point position, which we'll call a virtual reference station. And then from there, then it does a single base. It just does, it's as if you have your base station set up at that VRS, and you're collecting vectors in near real time from the VRS to your rover. So the base station or the VRS is variable depending on where it decided to assign that point position at the time you initiated your survey. On the right, you have what's commonly used in a Leica network, and this is what the ORGN uses, which is called a Master Auxiliary Concept, or a MAC. And in that case, it's a little bit different in that it doesn't assign a virtual reference station. Instead, it still processes, you're still doing baseline processing in real time between the rover and what's known as a master reference station. So when you sign in, again, it searches for a nearby cell of base stations near you, and then it picks generally the nearest station as your master station, and it does all the baseline processing from it. So you still end up with a vector from your master reference station to the rover. Okay. Although these two methods are different, both of them produce similar results in terms of accuracy, and I'll show that here today. So it's probably don't need to get too hung up on it. It's just important to have some understanding of what's going on. Okay, next slide. Okay, so the objectives today, and I'll show you some of the results, is we have two objectives. First, we want to evaluate the accuracy of RTK observations from an RTN. We're going to compare network RTK versus single base RTK. We have data from where it was collected with both GPS and GLONASS versus just GPS alone. So we'll do those comparisons, and then one of the research questions we were trying to decide is there an optimal session duration? So how does it compare in terms of accuracy when you do a 5-second shot versus, say, a 3-minute shot versus, say, an 8-minute shot, and so forth. Assuming that it was of sufficient accuracy, which it is, you'll see it is, the next step in our objectives is to then develop a method where we could use RTK in a geodetic survey campaign with the goal of achieving 2-centimeter or less ellipsoid heights at 95% confidence. So we want a repeatable campaign-style survey where we can tie it to the cores and do a least squares adjustment of our total survey network. Okay, next slide. Okay, so to get started, we began using data from a survey that was done in Oregon, and then we also used data from a survey that was done in South Carolina. Now I'm going to focus my talk mostly on the survey in Oregon, simply because I'm talking to Oregon surveyors, but understand that most of the steps I'm working through were repeated when we analyzed the data in South Carolina. I will show you the results of both, though. So starting with Oregon, we began by analyzing a survey that I did actually in 2014 that involved 18 existing benchmarks, kind of surrounding Corvallis, Benton, and Linn counties. On all 18 of these marks, we did 3 to 10 10-hour static sessions on every mark. And the purpose of that was to derive really highly accurate coordinates on each mark from a conventional static survey campaign so that we could use those coordinates as a basis for evaluating the accuracy of the ORGN. Okay, and then during that static survey campaign, we actually used a feature in the Leica data collectors I think it's called auto points, where you could set it up so that actually while you're doing a static session, it also simultaneously logs single epoch RTN observations from the ORGN. And we did this using different settings, like say for the first day we connected to the full network and just collected GPS only. And then day number 2 we did GPS plus GLONASS from a single base station. Day 3 GPS only from a single base station. And what would have been neat is if we had a day 4 where we did GPS plus GLONASS for the full network, but at that time that wasn't available in the ORGN. Okay, next slide. Okay, some of the sites, most of the sites, I'd say 15 or so of them 15 of the benchmarks were in good locations, clear view of the satellites, minimal trees, these really suitable sites for a GNSS survey. But we also purposely collected data at a few bad benchmarks just to see if, because we wanted to simulate real-world conditions, trying to recognize that there are times where marks are not in perfect places and you end up having to make measurements at sites where there's some trees or signs. So 2 of the marks were next to signs, traffic signs, and then 1 was actually kind of next to a wooden telephone pole. So not all of them were perfect conditions. We're trying to get a nice cross-section of situations so we have conservative results. Okay, next slide. Okay, we took the static data, all like I said, the 30 to 100 hours of static data, and we post-processed all of it in Opus projects. So there's a little illustration there on the left of how to do that. This is using a network design that NGS is currently recommending when you use Opus projects, called a hub and spoke network or a hub network. And in such a network design, you take one active station near the middle of your session and you designate it as the hub, which is depicted in orange as an orange circle on this diagram. And then add data from numerous cores and then process all baselines from the hub to all the other marks in the session. Okay, so we did that for every session in our survey, and the figure on the right it shows in blue the baselines that were processed from our hub, which we use as core, to some nearby cores in Oregon and Washington. And then if you look at the figure in the bottom right, all the baselines then radiate out from core to all the marks. And so I'm not going to spend more time talking about Opus projects, but just to say we used Opus projects to derive really highly accurate coordinates on all the stations so that we could use those coordinates for evaluating the RTN data that we collected. Okay, next slide. And we then took and prepared the RTN data that we collected. And as I mentioned, at the time we collected a continuous stream of 1 second single epic observations for the full 10-hour session. And when I say observation, I mean those Earth center, Earth fixed, delta x, delta y, delta z components for each vector, and then also their variance covariance matrix. Next. And we had RTN data files for each mark. We had 3 of them. We had one for these different settings as shown on the slide, whether it's SRTK or NRTK, and then whether or not we use GPS only or GPS plus GLONASS. Next. And the idea was I wanted to combine these single epics into a multi-epic solution. And that's what you guys are probably used to doing, is you would set up your rover and say do a 180-second shot. And what it is it's taking all those single epics and it averages them for 180 of them and gives you a final coordinate. And so I wanted to simulate that using this 1 second data, and for a range of observation intervals. So we wrote a script to do this. What it would do is it would divide each data file into 40 windows, and then they were each about 15 minutes in duration. Then we selected a sequential number of fixed single epic observations, so no floats. And if it was floating, we discarded it. And then we created 40 5-second shots throughout the day, 40 30-second shots throughout the day, 40 1, 2, 3, and all the way up to 40 15-minute shots at each mark. And then for each of these 3 different settings, SRTK and NRTK. So ultimately, we ended up with over 1,000 RTN shots per mark for analysis. Okay, next slide. We did the same thing with the data in South Carolina. As I mentioned, all the same steps. The only difference being, in this case for South Carolina, the surveyors actually took the RTN observations. So they stood there throughout the day taking 5-second shots, 30-second shots, 1 minute, 3 minute, 5 minute, 10-minute shots, and storing it in their data collector. And they did that for 3 days, and ultimately ended up with 360 RTN shots per mark with the different durations and settings spread out throughout the day for analysis. Okay, next. This is just maybe one other difference, I guess, in South Carolina. Some of the marks, I don't know if you can see it, how well you can see it, but there's these pictures with the black arrows are pointing to where the different marks are located. They kind of pushed things a little bit more in South Carolina in that survey than we did in Oregon. They set up under worse conditions than we did, so the data is just a little bit noisier as a result. Okay, next slide. Okay, so now that we have the static data for comparing it with our RTN data, the next step was we simply differenced all the RTN shots with our quote-unquote true coordinates from Opus projects, and that gave us, we could look at, okay, what's the difference in northern, eastern, and up between all these RTN shots and then what we would have gotten in Opus projects. And we resolved those into 2 statistics, vertical root mean square error, and there's the equation for it, the RMS, and then horizontal root mean square error. So assuming there's no bias between the RTN data and the static derived coordinates, BRMS and HRMS are good indicators of the vertical sigma and horizontal sigma of our data. So we give us a reasonable estimate of what the standard deviations of our data are. Okay, next slide. Okay, so I'm going to show you a series of curves. This is what we've been driving to. On the left is the vertical RMS. I'm going to plot it versus session duration. If you click one more time, it shows, okay, this first curve, this is the ORGN and full network corrections, and the vertical RMS So versus session duration. So, and each data point has over 18,000, is based on 18,000 shots. All of those 18 marks. So a lot of data, a huge sample size. What you can see on the black curve, it's kind of interesting to note how gentle that curve really is. The first data point on there is actually at 5 seconds, so a 5-second shot. And if you track yourself along it, if you do a 30-second shot or a 60-second shot, all the way out to about a 180-second shot, the curve hardly moves at all. So the difference between a 5-second shot and a 180-second shot is like literally like 1 millimeter, maybe 2 millimeters vertically, hardly anything. And then if you're willing to stand out there all the way up to say 15 minutes, which is the furthest data point on the chart, you know, it starts to improve just a little bit. You could drive it down by maybe as much as 5 millimeters. So bottom line is the accuracy hardly improves with session duration when using real-time kinematic algorithms. And I've found other papers that have shown that as well. So that's kind of interesting. The next curve up, as you can see, that is the single base RTK. So single base RTK is clearly worse than network RTK. And this curve in orange is just GPS only. If you click again, you see the same single base RTK, GPS plus GLONASS is slightly more accurate than GPS only, but neither of them are as good as network RTK. If we had a network RTK GPS plus GLONASS of the Oregon, we would probably see it beneath the black curve a little bit. Now the next, as Randy clicks, okay, now we'll start seeing the South Carolina data. Okay, this blue curve, that's South Carolina, network RTK, GPS only. Look at how closely it matches up with what we found in Oregon, almost identical, except for maybe one data point. Okay, click again, that's GPS plus GLONASS, so just slightly better than GPS only, network RTK. And then click 2 more times, Randy, and those show single base RTK, GPS only, and GPS plus GLONASS. So again, we're seeing a lot of consistency for the most part between these two networks, which is pretty interesting and encouraging. Okay, next slide. We could plot the same thing with horizontal. I plotted it on the same scale as the vertical, and you'll see all the curves seem to kind of band together, which is another interesting finding. And what I conclude from this is if you just care about horizontal, if horizontal is all you care about, maybe you're doing a boundary survey, you're not worrying about vertical, it doesn't matter what setting you use. They're all going to return similar results in terms of accuracy. But if you look closely, the 3 curves on the bottom of this plot are all network RTK, and the 3 curves up above are single base RTK. So network RTK is maybe slightly better horizontally as well. Okay, so next slide. So kind of to conclude, you know, RTNs in both locations produce similar results. Next. Here are the different accuracies that were plotted in those 2 charts. Network RTK is clearly more accurate than SRTK, especially vertically. That's where the biggest benefit is. In terms of horizontal, they're both fairly similar though. Vertically, NRTK is nearly half as small as SRTK. And so I kind of focused on NRTK because it's approaching the accuracy standards that I was talking about. So if you took those values, vertical RMS, and scaled them to 95% confidence, you could see, you know, about 4 to 5 centimeters, 95% confidence for a single observation. So clearly there's some benefit there. And if we started taking more repetitive shots, we could drive these errors down even smaller, and that's where we're headed. Okay, next. And GPS plus GLONASS is slightly more accurate than GPS only. We saw that. Next. And then accuracy hardly improves with session duration. You can interpret those charts however you want. It seems to me that somewhere around 3 to 5 minutes is kind of the optimal duration when you're balancing time you have to spend on a mark versus how, you know, the improvement in accuracy that you actually get. Okay, next. Okay, so implementation, the next step is we wanted to take the results and start thinking about, okay, how can we combine RTK data in a geodetic survey? And so this is the idea we put forward. It's called what we're calling a hybrid network. Hybrid meaning because it involves both RTK data and static data. So the first step, as shown on this chart, is step A. You first go out and you take shots on your project marks, so your control marks, your passive marks. And as you move around, if they're kind of spaced far apart, you may end up, the real-time network may end up picking different reference stations as you're moving around taking shots. So that's kind of what this illustration is trying to show. When you go to the office and download it, the next step is then to take the static data that's collected at each of the active stations from Part A and upload it to Opus projects, add cores, and then process those static observations to get static derived vectors in Opus projects. And then Part C is to simply just combine the two. Combine the network RTK vectors from Part A with the static derived vectors from Part B and get this combined network for adjustment where you can hold the cores. And all these vectors shown in C are measured more than once, definitely. So you have some repeat observations. Okay, next slide. So we wanted to put this to the test. So we returned to our original survey in Oregon, and we divided up the project into for three crews, each responsible to go out and measure 6 marks. And I think the next slide explains it a little bit better. Next slide. So here's kind of the field procedure. I deployed 3 crews. They went out and they simply just set up on a mark with their 2-meter fixed height tripod, waited for connected to the RTN, waited for it to initialize, and then they take a 180-second shot. Okay, and I click down. Then they inverted the antenna and made it lose initialization, and they reset it and took another 3-minute shot and repeated that. And then they would pack up their equipment and drive to the next mark. And they would do 6 marks per day, and they would loop around 3 times, going in between each of those 6 marks, so 3 revolutions per day. I click down. And what that did is it gave us 3 shots in the morning, afternoon, and evening on each station, and a total, since we did it for 3 days, a total of 27 shots. And I know that's way more data than you need, but we just needed something so we had data to work with to build our hybrid networks. Okay, next. When we downloaded the data, we noticed that it primarily, we ended up having vectors radiating out of 4 different base stations in the ORGN. So we went to ODOT's website and downloaded the static data files for those 4 stations, those 24-hour data files for 3 days. And we uploaded it to Opus projects, and we added 7 additional cores, and then we did all of our session baseline processing of the static data in Opus projects. Okay, next. And then we started building hybrid networks. And so we ended up, for Oregon, we ended up building 10 hybrid networks for testing. Of course, if you were to do this in practice, you would only need to build 1. We were just, what we wanted to do is see what happened if we did, say, 3 shots per mark versus 4 shots per mark versus 5 shots. So we were trying to figure out, how many shots per mark do we have to do to derive an ellipsoid height to less than 2 centimeters at 95% confidence. And so one of the key things when we were sampling our total number of shots per mark is we wanted to make sure for each network we had, we spaced out the repeat shots throughout the day. So we have different satellite configurations, and then also it ensured that there were independent setups and independent initializations. Okay, and then we did the same thing for South Carolina using both GPS and GPS GLONASS. We put the data in Opus projects. There's our network processing for the static data files, and then a closer up one you click down that shows a close up of the project area, and you can kind of see the 4 stations in the ORGN and then these RTN vectors radiating out of them to our observed marks. Okay, next slide. So you would think, okay, well, just now you've built your network, now just adjust it. It turns out there's one more detail we had to work through, and that was that, and this is actually a pretty big problem, and I hate to even mention it. It's just so important though that I have to, and that is that we're combining vectors from two different sources. We have one source from the RTN and the other from Opus projects, and it turns out the variances and covariances of each of those vectors are drastically different. And you see this all the time. Actually, different software programs have different scales to their variances and covariances. And there's a nice study done in 2004 where a guy processed a network in Bernice software and then in Gamut, and he found drastically different scaling of the variances and covariances as shown in that table on the slide. So you have to do something about that before you can just combine and adjust the networks. Next slide. So what we did is we used this thing called variance component estimation, and what that is you first adjust just one source of data. So say you just adjust your RTK vectors, and you iteratively scale the variances and covariances of those vectors until you get a standard deviation unit weight equal to 1 for your adjustment. Then you do the same thing for your Opus projects vectors until they get to a standard deviation of unit weight equal to 1. And now once you're satisfied that both the variance covariance matrix for your RTK and your Opus project vectors are scaled properly, then you can just put everything together and then do an actual adjustment. And next slide actually shows, this is the full workflow. If you want more details, it's probably too small a text, so let's move forward to the next slide. When you put it together and adjust it, you should expect that your standard deviation unit weight of your adjustment should still equal 1. And so we did minimally constrained and fully constrained adjustments shown in this table MC and FC for each of our hybrid networks, and you can see it. In all cases, they're very close to 1. So we were kind of satisfied that we had properly scaled the variances and covariances. Okay. Next slide. All right, so the final slide, this is kind of the final results. So we took, say, the networks where we only had 3 shots per mark, and we adjusted those. So 3 RTK shots per mark. We did the adjustment of the hybrid network where we only held the cores as control. And these are the estimated errors at 95% confidence. The chart on the left is vertical. So all the 18 marks, they were somewhere between 1.3 to 2.1 centimeters vertically in terms of ellipse side height. And then the chart on the right shows what the formal accuracy estimates were, pretty much all sub-centimeter horizontally. Okay, and then we looked at, okay, well, what would happen if we did 4 shots per mark, and then we adjusted those networks. So if you click again, you'll see it tightens just a little bit more, okay? A little bit more accurate, a little bit more precise. How about 5 all the way out to 9 shots per mark? And you get this nice smooth curve here. And then we did the same thing with the South Carolina data using GPS only and GPS plus GLONASS vectors. And if you click one more time, you can see all of it. So that's kind of our results were, so say, okay, now I want to write some sort of surveying specification and say I want it to have an ellipse side height to 2 centimeters, 95% confidence. How many shots per mark do I need? Well, based on this chart, you can interpret it how you want. Looks like GPS only South Carolina network seems to be the worst condition. Maybe 6 shots per mark is a very conservative estimate. You could probably argue that 4 shots per mark is enough in Oregon. Okay. Next slide. So to kind of wrap this up, I'm excited about this technique. Hybrid networks definitely increase efficiency. The field work is doing the RTK surveys, and then you take advantage of the data from your active stations to do your static processing. And it kind of falls in line with how I've always done surveys when I used to work for the BLM. We would, when I worked for the BLM, our typical conventional approach was when we start a survey, we'd use Opus to establish control at a few stations. And in this case, in this example, I'm proposing that we take that a step further and use Opus projects. And then you fill in and densify your network using RTK. And that's kind of how we used to do that in BLM. And you can see what accuracies can be achieved. And next. You got to account for the variable scale of the VCV matrices, those variance covariance matrices. That's a technical detail that probably deserves a lot more discussion than I'm giving here. Next. Here's just some results in terms of formal error propagation, like the charts are showing, just summarizing what accuracies can be achieved. That, really, the more shots on per mark, the more you can drive those accuracy estimates down. And then we also compared our hybrid network coordinates with our static-only network coordinates, and that summarizes some of those results in terms of vertical and horizontal RMS. Next. Lastly, if you want a conservative guideline, 6 3-minute shots per mark, space those out throughout the day, get independent setups, but I'd say maybe 4 to 6 shots per mark is probably sufficient to get an ellipsoid height to less than 2 centimeters. 95% confidence. Okay, next. Okay, so where do we go from here? Very recently, I was just named to be the project manager for developing routines in Opus projects so that you can actually load your RTK observations straight into Opus projects and then build your hybrid network and adjust it. And hopefully it'll take care of all this business of scaling variance covariance matrices for you. So it'll be hidden in the software. And I'm excited about that opportunity, and I'm hoping that it will really, really make things easier for people to get high accuracy ellipsoid heights. And then the whole idea is that you can then take those surveys and then submit them to NGS for publication. We're doing more testing in Maryland right now, and we are also working on writing some specifications for how to do this. Next slide. Here's just a simple diagram of what it would look like. This is just a mock-up. In Opus projects, you first load and do your static baseline processing, and there'd be another tab that you could click. I don't know what we'll call it yet. For argument's sake, let's say RTK. Click on that, and then you could then upload your RTK vectors into your network. And we're also adding other modules for adding other types of observations like total station and leveling. Next. So I want to acknowledge all these people that have helped me with this project. It's certainly not me alone. My students, Mike Olson at Oregon State University, Michael Dennis, Mark Armstrong, and also ODOT for providing us access to the ORGN and even help with some of our equipment. And with that, I'd be happy to answer any questions.
Well, Dan, I have one question for you. And do you have a reason why South Carolina seemed to be slightly have more error than what there was for the in Oregon?
Yeah, I think when the South Carolina survey was done, they kind of made it a point to measure marks under trees. They set up in sites that were quite a bit worse than what we did in Oregon. So some of the data was kind of noisy as a result. So their curves are probably more conservative. The other thing is, what I noticed was, I don't know if it was clear in my presentation, but we did 2 campaigns in Oregon. We did a 2014 survey where we were doing the single epic shots. And then we returned in 2016 and actually took and executed a hybrid survey where we took the true 3-minute shots and built the thing. And I noticed the 2016 data just was much better than what we collected in 2014. I don't know why that's the case, but it just was. It was more accurate and more precise. So, and we were kind of seeing it in those charts. So we must have just had a good week of weather when we were doing it, or maybe that's a possibility. I don't know.
Did you do any comparison between, was the South Carolina one VRS network, or is it a Leica network also?
Great question. I wish I had made that clear in the talk. Yes, the South Carolina network is a VRS, and of course Oregon is a MAC. And so yes, those comparisons were done. But I will say we've only done 2 states so far, right? We're right now working on another set of tests in Maryland, which involve, in Maryland we actually have two independent real-time networks that cover the whole state. And we're going to, and one's a VRS and one's a MAC, and we'll add those into this study when we're done. But what I can say is it seems that either method seems to produce similar results so far.
Excellent. So there is no preference of one network over the other.
Yeah, I mean, I can't really see it. I mean, I think if maybe you could make the case, you could argue that the Oregon data looked a little bit better, so maybe that's because it's using the MAC method. But I personally think it has more to do with they were setting up under these big trees in South Carolina when they did their study. So I think it has more to do with that. There are some other papers that show VRS and MAC are similar too, so it's not just us finding that.
Great. I haven't seen any questions come in from any of the other people listening to this presentation, so we're going to end at this time. If there are any other questions, please email them to me, and I will forward them on to Dan, and we will put out a list of frequently asked questions or questions about this presentation, and hopefully Dan can give us some more insight on how to process mixing RTK with other data.
Yeah,
thanks.
That sounds great. And I wanted to say one more thing. We have reports on all of this material as well, and I'd be more than happy to share those reports or write-ups with anyone that would be interested and get a lot more detail than what I could give in a 1-hour talk.
Great. Well, I would like to see that for sure, and see some of the data that you've come up with a little more detail. So thank you, Dan, for presenting for us today, and we'll end at this time.